Okay, hello everyone. Today I'm planning to talk about the Higgs mechanism. And you may wonder why am I even recording this? There's so many intuitive explanations of Higgs mechanism already present in the internet, so it's not clear why do we need another one. However, I have some problems with them. I would say I don't quite like them, and I would like to explain why at first. So let me share a screen. So if I just type in Google something like intuitive explanation of Higgs mechanism, there's even like AI generated response. We could read it, or there's like maybe videos and articles here as well. And by the way, it's actually funny. I was planning to record this video a couple of times on this week already, and every time I was kind of getting distracted and doing something else. So I was preparing this search line in exactly the same form already multiple times, and every time this AI explanation was getting worse. I don't know why, and again it's within days. So yesterday, for example, he had like three analogies here, not one, and they were all better. um, there was an analogy with something like, imagine a body moves through viscous fluid, and there is a bit of fluid stuck on it in some sense, so it got heavier, right? I would say some problem with this explanation is that, in the Higgs mechanism, the initial mass of a particle, which we'll be talking about, is zero. So it's kind of strange, because we see that the difference is not just a quantitative difference, it's a qualitative difference, right? Going from zero mass to non-zero. And also this type of explanations, which I hear a lot, like, oh, imagine it's difficult for like a ball to travel through, I don't know, some sort of medium like a sand or liquid. They refer to dissipation intuition, right? They're essentially dissipative usually. Like, we think about them like this. Okay, so there is some friction there, and the ball loses energy, right? But the actual Higgs mechanism is non-dissipative, of course. So this intuition, in some sense, wrong. It's kind of misleading. There was some sort of analogy with celebrity moving through a crowd of fans, and everybody want to talk to him, so they all kind of surround him like a cloud and make it difficult for him to move. Basically, it refers to the idea that in the particle physics, that interactions give particles mass, right? The particles not just travel on its own, but it's traveling with like a coat of other particles, which makes the original particle heavier. This new particle is called quasi-particle. So this is kind of relatively precise, but it's not really Higgs mechanism specific. And in fact, to be honest, the phrase, oh, that's happened because of particle interactions, could be an answer to any question asked asked to theoretical physicists, right? Because, well, yeah, everything happens because of particle interactions. It's not really specific to our concrete situation. So yeah, it's not that bad, but I'm hoping to get something better. There's also some videos like this one, from PBS spacetime. But he's literally just writing down Lagrangians. Like I start watching this, there's tons of Lagrangians, and honestly, I think Lagrangian is one of the most like counterintuitive notion in physics. Right? Like what it even is. It's like the Hamiltonian is at least like it's like it has a meaning of energy in of the system. You could at least say, well, oh, it's like energy, it's like conserved. You could refer to some people's intuition. But with Lagrangian, you can't even do it. So it's like if you're a science communicator, you kind of forgot to communicate, right? Where's the communication part? And honestly, I didn't even quite like it. Haven't watched it fully yet, but like say even here, he says something like this.
The exact phase of the quantum wave function from one point in space to the next, local phase, doesn't affect measurable quantities, only relative phase matters. When we enforce this requirement, we find that we have to add a new quantum field to the Schrödinger equation that lets the universe counteract these phase shifts. That gauge field turns out to be electromagnetism, and oscillations in this field are the photon.
Well, basically, okay, then I could ask a question if electromagnetism has something to do with phase ambiguity in quantum mechanics. Well, that means if I have like just a non-charged scalar field and I consider one particle wave function of it, are you telling me that what I will not have the phase ambiguity in it? I will not be able to multiply it by some arbitrary phase and get the same state? There's no need for electromagnetism with an uncharged scalar field, right? I would say it's not clear what he means, but it works, right? This is somewhat confusing. But this is like a side remark. I don't want to get more into this video. I'm just explaining you why I decided to record this one. Basically, because all of that, I made a decision to come up with an explanation which will be fully precise, but at the same time fully intuitive. So I'm picking up a challenge of giving you fully precise explanation of the Higgs mechanism without writing down a single formula. So there will be no formulas in this talk, but the idea of the Higgs mechanism which you'll learn at the end will be precise. It wouldn't be just some sort of analogy, just what Higgs mechanism is. Yeah, it's a bit, it's not that easy task and it takes some time. I'm planning to do it in 2 steps. Step number 1 will be explanation of the notion of mass of the field, because it's not actually as intuitive as you may think. And step 2 will be the actual Higgs mechanism. So let me share my notes and I'll proceed to step 1. Okay, I hope it's working. So let me write the headline. Step 1, mass of the field. In order to explain the mass of the field, I will be using what's called mechanical analogy for field theory. That's very easy for people to work with. Let me consider the following mechanical system, which again very easily for you to imagine. Consider a chain of metallic balls connected by springs lying on a table. Let me draw a table like this. Okay, and balls are spherical, and the springs, they satisfy Hooke's law. So basically, it's a linear response. Springs. I will be calling this model A1 because this chain of atoms will model our one-dimensional field theory. Actually, should I say maybe 1 plus 1 dimensional? The direction, this will be direction x, this will be direction y. So the x direction of the chain will become our space direction in our field theory, and we also have, time. So let's try to consider, simple dynamics in this chain. Let me do the following operation. Imagine now for simplicity I'll be looking from above. I'll took one ball and I moved it to the right a little bit, and I hold it still here. So this spring is now compressed, and this spring is now stretched. What will happen if I am holding this ball like by hand? Well, it's very easy to understand, right? This spring contracted, now it will push the next ball, and this ball will contract the next spring, and this spring will push the next ball, and so on. And it's easy to see that this process never stops, right? This wave which I created, it will travel to infinity, right? To the or till the end of the chain, basically, because there is no new equilibrium position for this chain where not all balls have moved some finite distance, right? So the excitation travels to infinity. Now, actually, as our chain is lying on the table, we could consider shift in shift of the ball in the perpendicular direction, right? This is x and y. What will happen if I move one ball from equilibrium position up like this? Right. Well, okay, it's also easy to see that this spring is now stretched, right? So it pushes this ball to the left and up, right? And this spring, the force it generates could not compensate this one, right? There is an uncompensated force dragging this ball up to the right. So it will move here. After that, again, it will basically create the same situation for the next ball. And this means the next ball have to move as well here. And again, it's easy to see that this process has to continue to infinity. There is nothing which could stop this propagation, this process. There is no new equilibrium position for this chain in which not all balls have moved to some final distance. Hence we found basically in this simple model of a chain of balls lying on a table. The table, by the way, is frictionless, right? It was important. It's just friction, everything gets destroyed. Now, but we're considering frictionless table. We found two modes which propagate to infinity. That's actually called an example. There's a consequence. It's a consequence of the what's called Goldstone theorem. It states that for every spontaneously broken symmetry of our vacuum, there will be a massless mode. Yeah, I mean, I want to be precise here and say that, okay, the theorem has certain assumptions and certain limitations, so formulated in a certain context, but let's say we'll always be working in a setup where at least the idea of it, the main idea of it is true, holds. So these modes which behave like that, which propagate to infinity when they're created at a single point, they are called massless modes. And the symmetries which I'm talking about, in this case, it's shift symmetries. Let me explain to you what I mean. So when our chain was lying on the table, all balls were at certain positions, right? Now the initial positions didn't matter. Right? By this I mean, if we shift all our system, all our balls simultaneously, say to the right or to the left at a constant velocity, right, without compressing or stretching any strings, the energy of the system does not change, right? We could just move them like that, like a train, right? Springs are not compressed, so energy is not used for it. And the same for the movement in the y direction, to the front, right? Again, we could shift them like this. Without without the need of any energy pump. That's what I mean by symmetries. And the fact that they're spontaneously broken by the vacuum, by the choice of vacuum, in this case just means that, well, in reality, we had some initial position for those balls. We had the choice of the whole line, where to put them, right? Here, 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 but we put them at some specific location. And this is our ground state of the chain. That's what it means for the symmetry to be spontaneously broken in the vacuum, by the choice of vacuum. Maybe it's a bit confusing here, so I'll give you a better example down below. but here you just need to see the main idea, and that we had these two symmetries in our chain, moving to the right and moving front back, right left and front back, and the choice of vacuum breaks them spontaneously in a sense. And to each of the symmetries now we have a corresponding massless mode. And you could say that the theorem is almost a tautology, right? That precisely because we know that it takes no energy to move balls just coherently in parallel with each other like this, there should be this movement of them, this wave, which doesn't require any energy. Think about it like this. Of course, for when you move any ball which has non-zero inertia, you have to apply energy, right? It's kinetic energy, right? But what I mean is, ask a question whether the energy necessary in the limit of its velocity going to zero will be zero or not. And in this case, it is zero because there is no barriers for the whole chain travel like this in parallel, right? So if I draw a graph of energy of my excitation as a function of momentum, in the limit of momentum going to zero, the corresponding energy will hit zero as well. Okay, let me give you example which be a little bit closer to our real world, one step closer, so to say. I will be calling it A2 because it will be kind of two-dimensional. Imagine now we have the same table, but instead of just chain of balls like we had before, we will have the whole carpet like this. Okay, continues. Now our balls, yeah, they could still move in two directions. They could oscillate like this, could oscillate like this, but now there is like two-dimensional area of them. So again, in the limit, far away from the system, when we don't see already balls, we just only see the waves which could be created on this carpet. We'll see some sort of two-dimensional media with these fluctuations, which will be precisely described by some two-dimensional field theory now. Now that's what we mean by the mechanical model of field theory. Because in the infrared limit, this model become the field theory. Here I would like to point out that basically our first example was called a vector field. This is a notion which we will need in our Higgs mechanism. As I said, the number of space dimension of the field is of this field theory is 2, right? And the number of directions in which each ball could oscillate is also 2, right? So two-dimensional. What I mean is that our ball oscillate in the physical directions. That's what we mean by a vector field. Because at every point we specify a vector in our space, right? Oh, we shoot the ball, we could shoot the ball here, we could shoot the ball here, we could shoot the ball somewhere like this, right? And we could shift it in any direction in our space, right? So in the continuum limit, you would have a vector of shift for every point. As opposed to just, one number, how it could be for, scalar field. Big number here, no small number here. I know how to draw values. Think about, densities or something like this. Densities of whatever quantity you want at every point. For example, temperature at every point is an example of a scalar field. Here, again, in this system, we will also have waves, right? And again, there will be actually two kinds of waves. Again, from above, view from above. I could shift the whole line of balls like this to the right, compressing those springs and stretching these ones. And this wave of compression will travel in the x direction, right? Again, but the same principles. These balls will move these ones, these balls will push these ones, and so on. They'll just travel like this. That's one type of wave. Another type of wave is when I shift the whole line vertically, like this. And what will happen again? This spring got stretched. This means these balls have to move up, 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 right? They will move the next line, and the whole carpet will have to adjust. And again, the wave will travel into the x direction, but my balls will be oscillating up and down, right? Oh, sorry. In our case, they're on the table, so back front, right? In the y direction. I call it y direction. So the wave where the vector of field oscillation, field intensity oscillation, is parallel to the direction of travel is called longitudinal wave. This one is called longitudinal wave. And the one where this vector of field strength oscillation is orthogonal to the direction of the wave travel, like here, is called transverse wave. These are standard notions, but again, we will need them for the Higgs mechanism. So I would like to introduce them here in this simple mechanical analogies, where I guess nobody is lost yet. You all could imagine them very easily in your mind, and you see what these waves are. You could ask me, well, okay, but why I'm moving the whole line? Isn't it fair? In the previous example, I was moving just one ball. yes, you could make like some sort of spherical waves. There will be just combination of these two in some weird ways. These are just the main one which I would like to focus on, be the essential for us. Flat waves. Now also it's important to point out something here. Why I was not calling these two types of wave here, which we had, this one and this one, you know, this bulge here, transverse and longitudinal. Could I have already called them like that? That, strictly speaking, would be a bit inaccurate, because I would like to emphasize here that in this example, in the infrared, when I look from very far away, I'm modeling a one-dimensional field theory, 1 + 1 dimensional, which means by definition could not have longitudinal and transverse wave. The vector field in one dimension is the same as scalar field. The one-dimensional vector just one number, right, more or less. So yeah, at every point I specify a number or a vector. It doesn't matter. However, as I said, we still have, because it lies on the table, it's embedded, this two-dimensional space, the balls could oscillate, you know, like this and like this, right? However, from the point of view of this one-dimensional system, this is called internal direction. It's not physical. There is no movement happening of this ball in the direction of our physical dimension. So it's not actually a vector field. It's just two independent scalar fields. That's all. That's what we call internal dimension, internal symmetry. This is just the idea that we basically could consider, you know, multiple fields which, I don't know, could be related to each other in some complicated way. Not all fields have to oscillate in some physical direction, basically. I just want to make it clear. This notion of internal direction is also actually important for the Higgs mechanism, which we'll see in the real world in the standard model. Because the fields there, jumping ahead, I should tell you, they are both vector fields, but they also oscillate in this internal direction. So these two notions, which I introduced for you, they will be combined into one. You will have a vector field, and you also have sort of say collection of those vector fields transforming through each other in a certain way. Okay, I just don't want to make it more complicated, but so far your main takeaway should be that we consider the one-dimensional field theory with internal direction and a two-dimensional field theory we just have a vector field. And in all cases, we basically create a fluctuation at a certain point. It will propagate to infinity. The information about it will not be lost. It will travel infinitely far away, both in system A1 and system A2. And in system A2 we have two types of waves, longitudinal and transverse. And again, it's not crucial for you in some sense, but in both cases, this what's called massless modes, they came from spontaneously broken symmetries, in a sense that the carpet again could be moved left, right, and front, back, and if you don't compress or stretch the string, the energy doesn't change. So this massless modes emerge because in the vacuum you choose a specific position for every ball. If this is not very clear, I want to give you one more example of a massless wave of a different nature, just so that you don't have to stick with all this. It's the only mechanical analogy. So you see that field theories could be different. We'll call it P1, for example. Imagine a chain of one-dimensional chain of magnets attached to some points in space. Like this. Now you could ask, what is this strange thing? Physically, think about it like that. We have what's called iron core, the lattice of atoms, basically actual atoms of the crystal lattice, which have unpaired electrons on their orbitals. The electrons have spins, and the spins, they create this magnetic moment. So this electrons sit here, and they create these little magnetic moments. So these magnets, yeah, the magnets I will draw just as arrows from now, arrows pointing in the direction of the magnetic field which they create. Okay, so like this. We'll replace it with an arrow. Okay, from now on, the position of atoms are fixed, but the spins, they feel each other, right? We know that two magnets, they want to be aligned, right? Actually, it's also important for this particular approximation which we are working in, that only the neighboring spins feel each other. In reality, of course, it's not true, but for simplicity, we assume that these two spins already, they don't know about each other. They're too far away, and the field just, the field decays with distance. So assume that they don't feel each other. Only the neighboring spins interact. Yeah, the magnets will be calling spins from now. And this model is called a spin chain. So yeah, and without any problems, we could consider model it's like B2 when you have again two-dimensional lattice of these spins. Sitting here. Or B3, three-dimensional lattice, that's already actual model for actual magnetic, and so on. If you want, you can continue it as much as you want. I choose this model because I want to show you the notion of spontaneous symmetry breaking in a more clear way. And here, what we see, how you can ask how the vacuum of the system will look like. What the most preferred position for the spins in which the energy will be minimal. Well, it's clear that they all have to be aligned with each other, right? Because if they don't align, we see that, well, they want to be aligned, right? So they all have to be aligned. But essentially in this approximation, they don't care which direction they'll be pointing to, as soon as they all point in the same direction. Basically, it could be, just all of them up, all of them down, all of them pointing, slightly like this to the right. So basically we have the whole two-dimensional sphere of possibilities. And it's just one sphere because they all have to look into this direction at the same time, otherwise the energy will not be minimal. So the ground state, the state with minimal energy, is parameterized by the point on a sphere. And in the concrete, vacuum state, some specific point will be chosen. Usually it happens spontaneously, right? And the material have spontaneous magnetization. That's how magnets work. You just have a piece of ferromagnet and it already works as a magnet. It has some magnetic field macroscopically, because all of these little spins, they align with each other, right? And they start pointing in one direction, and this creates this strong, big magnetic field, right? So that's here. I just wanted to make this idea of symmetry breaking more clear, because now you clearly see there was a symmetry which was broken by some choice. And in fact, here you will also have a massless mode. Yeah, it's called a spin wave. Imagine what will happen if in this scenario I will move and this where they say all pointing up. I will rotate one spin a little bit and I will hold it like this and rotate it. Well, the neighboring spin will feel him, right? It's like he'll also want to rotate to the right, right? So we'll have to rotate as well. Then the spin next to him will also react, and we'll have to rotate a little bit. So they all have to move. And again, if you think about it carefully, you see that there's nothing stopping them. It's just this excitation which I created, it will propagate to infinity. So we'll have a massless spin wave. In the system. So for now, I was only considering massless modes, right? Massless waves. But I promised you I will explain you what the mass of a field is, right? So far, it was building up intuition of what the massless field is, what's like, absence of mass is. And now I'll explain to you what the mass is, right? Okay, so consider now the system which I will call C1. It's very similar to A1. Just imagine we have this one-dimensional chain of balls connected by springs. We lift it up from the table and we hang each ball from the rod, attached to some, rail, like this. Draw it. Basically, let me draw my rail. There's these pendulums, rods, hanging from it. So each pendulum, each rod, attached to this cylinder, which could rotate freely on the rail. So basically, each pendulum could oscillate like this. And here on the top of the pendulum, I will have my balls, these metallic balls hanging, still connected by springs. Okay. Such a quite interesting system. So again, you could each ball could wiggle it a little bit with the corresponding pendulum, and the neighboring ball will still feel it because of the spring. The spring feels any stretch. And now I could ask the following question. Okay, could I do the same experiment, perform the same experiment I performed for model A1, which is I'll take one of these pendulums and I swing it a little bit away from its equilibrium position, right, to the right. Make it create this kind of little deviation like this. Hard to draw, but I hope you get the idea. Right, just take one pendulum and pull it like this. Yeah, what's going to happen? This is actually very interesting and very beautiful. And luckily, I mean, it might be counterintuitive, but luckily I found an actual video for you with somebody actually building this chain and showing you what's going to happen. So let me stop sharing this. Okay, here we go. Hope you see it. So here's the model. Well, as you can see, he has the pendulums, and I'm not sure you see the springs. They're not springs, they're just strips, but they do the work, right? They do the same job. I mean, they resist stretching. And also, he has an engine there, and at some point he will turn it on, and this rail will start rotating. Ignore this for a second. I mean, this video is dedicated to a completely different topic. It's the topic of solitons, and this wave equation, this field theory which I described in here, is actually way more interesting than you might think. And this notion of soliton by itself is also probably way more interesting even than Higgs mechanism, and maybe I will talk about it one day, but not today. So he'll be trying to demonstrate solitons to us, but we'll only focus on the first seconds of the video, where he'll just raise one pendulum, just, accidentally. Look, you see? Well, okay, here you really turn on the engine. Before he turns on the engine. Yeah, well, here the engine is turned off. So he raised the rod, and unlike the previous model A1, as you can see, the rods at infinity, so to say, far away from this place, they don't feel anything. They're not raising up. The whole information about the fact that here he just raised the pendulum a little bit at some final angle is completely lost as soon as you move far enough away from it. Completely unlikely, completely in contrast with what we've seen in our first model, when the balls were just sitting on the table. So I hope you enjoyed the video. Let me probably close it because I'm not gonna need it anymore. Yeah, if you want to see the soliton, yeah, the soliton looks like this. But again, that is a topic for a separate video. For now, let me just go back and explain you what you've just seen. Okay, let me share screen again. So yeah, as you probably have seen that when you raise one pendulum, the neighboring pendulum also raised a little bit, and the next one raised too, but already on a smaller angle, and so on. And basically the next one was raised even lower than the first one, and so on. The angle was constantly decreasing with distance from the initial application force, initial excitation. So what the difference here? Why is it happening? Well, it's not that hard to guess. If I consider the same force diagram, yeah, you will see that now, if I, let me, again, view from above. When I swing the pendulums, there will be a force of gravity acting, on the ball, which will be compensated by the tension of the rod. And this force of the rod tension will have a non-trivial projection on the horizontal plane. Let me even make it more visible, make it stronger. You see, despite the fact that this spring is pushing the ball in this direction and this spring is pushing the ball in this direction, this force is now compensated by the rod tension. And yeah, it's true, we have to swing this pendulum a little bit, right, to gain a little bit of this force. But with each next step, with each step, we'll be needing less and less of it. Here you already almost will not see it, because this is already almost equal to this one, right? Almost aligned. So if we draw it big, our solution from above looks like this. Oi, took a screenshot accidentally. So the forces are getting compensated by the rod tensions. Which allow us to swing every next pendulum on a smaller angle than the previous one, making sure that excitation will decay with the distance. In fact, this, if I draw this deviation angle as a function of distance from original point, it will be decaying exponentially with distance. This exponential decay of point-like excitation with distance is the mass of the field, actually. That's what we basically call, the mass of the field. Well, you could ask, and what was why did it happen? What was the difference? What did we have here that we didn't have there, right? Basically, we have this rods and this force of gravity, right, which was returning the rods to the equilibrium position. Yeah, whereas in system A1, in the line on the table, there were no actual equilibrium position. These balls, they were different to where they are on the plane. As I said, there was a symmetry there, and now the symmetry is gone, right? On the frictionless table, you could have moved them like this, and it wouldn't cost you anything. But here, if you want to raise all the pendulums simultaneously, you are paying the price, right, in terms of energy, because you're doing work. It requires you work against the field, gravitational field, right? You raised each ball higher than it used to be, so the potential energy is now increased. So even if the springs are not stretched or contracted, you don't have asymmetry anymore. and that's why you don't have a corresponding massless mode. Think about it like this. If we want to again create a wave there with some momentum, what the energy required for this wave will be as momentum approaches the zero mark. In the A1 model, right, the model on the table, this energy was zero, precisely because, yeah, if you move the ball spiral really slow, and you know, so the kinetic energy is becoming zero, it doesn't require you, it doesn't take you anything. This direction or this direction, right? You don't have to put any energy into it. But here, even if you're moving them infinitely slow, like you still have to fight off the gravity. So this means the spectrum of this excitation, the energy as a function of momentum, will now look like something like this, because in the limit, the momentum of the wave approaches zero, you will have non-zero value energy required, and this value is called, this value of energy is called mass, right? That's what the standard definition of mass is, which is related to this exponential decay here. Yeah, I promise not to write any single formula, so again, if you don't want this, just ignore it. Just say I need the same mass. Just one is the position space understanding of mass, and another is momentum space understanding of mass. So yeah, this is massive versus massless, which I drew before already. Oh, little mass. Okay, I hope it's clear what's going on here and why the field now behaves like this. Now I could go back to all my previous models and see whether I could, make them all massive. We already see that to achieve that, essentially what we need is for every ball in this chain to have binding potential, right? The ball which used to be indifferent to movement in any direction now need to have some sort of energy required to be lifted up. So let's do it for model A1. I would call it A1 fully gapped. This mass, this behavioral spectrum is usually called gap, because if this is the vacuum energy, which is zero, the energy of first non-trivial excitation is separated from it by a gap. That's what it's called, gap, right? And A1 fully gapped will mean that all of the modes which used to be massless now will become massive, so they're gapped. And that's easy to achieve. I just take my balls and I put them in this kind of little holes like this. Make holes in the table. Okay, and so on. Now what happens is that when you try to push this ball here, compress the string, right? Again, it takes some energy for this ball to be lifted, and this ball takes some energy too to be lifted. So we'll have phenomena similar to the one which I discussed here, right? There will be now a new equilibrium position for these balls. So this excitation which you create will not actually propagate to infinity. And the same for the movement in the orthogonal direction, in direction orthogonal to my chain. Because again, the whole is spherical. Do I move here, do I move here, I have to pay the price. So both of my fields which I had now became massive fields in this one-dimensional chain. And again, it stems from the fact that just a parallel movement of these balls, or perpendicular movement of those balls, like this or like this, costs me some energy, right? Because I have to lift every ball a little bit, like, right? That's compared to just moving them smoothly. And this energy is our mass. Now, because that's important for the actual Higgs mechanism, let me consider intermediate situations, which is also interesting. Imagine I put my system A1 into the groove, which I will call A1 transversely gapped, transverse gap. Just, a groove like this. And here are my metallic balls, leaving line in this groove. Now what happens is that the longitudinal wave is still massless, because I could do the same experiment as I did with model A1. Just press one ball here to push the next one, and so on. The symmetry of parallel transport in the x direction is still there. They're just moving in this groove altogether. There's no problem. So the longitudinal mode will still be massless. However, as I said, it's unfair to call it longitudinal, so let me put a quote there. As I already explained before, because it's not an actual vector field. But you got the idea, I hope. And the transverse direction are now gapped. You can't, because in order to lift balls up, you have to climb up this hill. You have to get out of this valley. Similarly, you can consider the alternative model where you have longitudinal gapped model where you have multiple grooves on the table perpendicular to our chain. Okay. So now again, the longitudinal mode is gapped, longitudinal, because you have to climb up the hill. But the transverse is not. You could just move, here and there. You could move the system in these grooves without any additional energy. So this type of wave, right, is still perfectly fine. It will travel to infinity. Now, why I'm doing all this, why I'm giving so many examples? Because these examples will allow you to build intuition for the situation which we'll actually need in the second half of the talk. I'm just saying it's precisely what happens in real world, where you have some fields in this internal direction due to Higgs mechanism, like literally here in the symmetry model, becoming massive, and some remaining massless. So that's important to understand that you have different possibilities. And in fact, in our universe, those fields which corresponds to weak interactions, they become massive, and that's why the weak interactions so weak and happen on such a small distance. And the electromagnetic ones, they remain massless, the electromagnetic waves, and that's why we see them. That's why you see them right here, right? They travel to infinity. Okay. Now, just to give you more intuition, and again, to take you a little bit away from this entirely mechanical analogy, let me probably consider model what B1, right? Or B2, which was our magnets which only feel the nearest neighbors on the resulting from a chain of atoms or a lattice of atoms. Okay, so remember, recall that there were massless spin waves here. Now, what will happen in the vacuum, right? In the vacuum, all my spins were pointing in some direction, which is again randomly chosen. Okay. Oh, sorry. I wanted to be on the same distance from each other, just to look nice. Okay. So it's all there in the vacuum. So what will happen if I apply external magnetic field? Basically, I bring a big magnet here, big strong magnetic field. So of course now all these little magnets, they would like to rotate in this external field. They will adjust their position, and the new equilibrium position will be fixed. Yes, we'll have to all point in the direction of this big external magnetic field. So in this case, all pointing up. This direction up is now the equilibrium position on the sphere. So basically, even if I rotate them all together to the right, like I used to be able to do before, it will cost me some energy because now they're not aligned with the external magnetic field. So now if I move one spin a little bit, right, it always wants to move back. So we'll have the same phenomenon going on here, right? If I rotate one spin, I hold it, the force, the second one, it will rotate, and the one after him will rotate even less, and this one will rotate even less, because, they all care about this field more now, in a sense. So this excitation which I created here will decay exponentially. This angle again, at which they have to rotate, it will decay exponentially. And the corresponding spin wave will become massive. So the single excitation decays, and it took non-zero energy for all spins to even rotate all together, because they're overcoming the external magnetic field. So as you can see, You don't have to stick to mechanical analogies. It could be something completely different. This idea of massive waves and massless waves, it extends beyond just, you know, balls and springs. So I think it's very beautiful. You could ask, well, okay, did I missed out on system A2, right? Well, I didn't quite. I mean, I could do system A2. In principle, I could do the same. I could put every ball of my carpet on this table into a hole like this, right? So now it will have a non-trivial equilibrium position to know how to draw it. And now it will be A2 fully gapped. Both longitudinal and transverse mode are now massive, right? For the same reasons. However, I wasn't able to come up with a good idea of how I'm gonna make, you know, only transverse mode gapped, only longitudinal one. Unfortunately, the mechanical analogy breaks down here. Of course, you could say, oh, I could put them in the grooves, right? See, put my carpet in the grooves like this. And this one in the neighboring groove. Yeah, but this basically it kills a transverse mode in this direction and a longitudinal mode in this direction. And that's all. And it's not clear what happens in any other directions, right? Say not exactly orthogonal or aligned with these grooves. So it's a really weird thing, and the anisotropy, it becomes anisotropic. The isotropy is lost. So this is something weird. I don't know. It probably happens somewhere in some sort of anisotropic crystals. That possible, something like that occur in nature, but not in the Higgs mechanism, right? So I don't know. It's like you think about it yourself. And now, what else I would like to say here is that we could already try to, you know, kind of introduce the notion of the Higgs field in these examples, and the idea of how exactly, you know, the mass comes from interactions of different fields. But it will be in precise analogy. Look, imagine my table is made out of rubber, and rubber could also stretch and compress. So I could create waves of compression here, and it will create this kind of bumps on it. I put pressure. And you know the height at which my rubber bar band sits above the ground, I will denote by function h of x. You know the size of my heel at each point. At each point I will have some sort of height. Just big here, smaller here, right? It's like this. H of x vary. This is precisely an example of a scalar field theory. Now you have my, again, chain of balls line on the table somewhere like this. These balls will feel these hills and valleys, right? And in fact, if there was a wave traveling in this chain of balls, and I also, by hitting with my fist on this rubber band, I created a wave of compressions in the field h of x, in this hills and valleys. They will scatter like this. So my freely traveling wave in the chain will scatter with the wave of rubber band. So one ball, it will be raised up a little bit, and because of that, the interaction which will transfer to the next ball will not be exactly the same, and the overall momentum of the wave could change. That's how the scattering of particles in field theory actually works. Okay, so that's how they interact. But now let's say I apply constant pressure on my rubber band, and I created all those ripples on it. Now my rubber band looks like this. So I'm constantly applying pressure on each side of my table. And my balls happen to live precisely lie in this, corresponding valleys. Just like in this model drawn here, right? So I basically reconstructed this model by applying constant pressure to my rubber table. That's what we call, the non-zero vacuum expectation value of field h of x at every point. So now in its ground state, this field H already has non-trivial profile. I could still, be hitting on it with my fist here or here, and then still create waves of these hills and valleys. They still, they could move, fluctuate, but in its ground state, there was already hills and valleys. And these hills and valleys already gave mass to my longitudinal mode here, of these balls, of this chain of balls here. So that's like really close analogy already, because now you understand what mass of a field actually is, you understand what different fields are, you see how they interact, and you see what's called vacuum expectation value of a field is, which is plays crucial role in the Higgs mechanism. That basically already in the vacuum, some field has some sort of condensate non-trivial value. In this non-trivial value, it couples to other fields like this, but they gain mass. Basically, these balls they now could not move freely because of this hills and valleys created, which is like stationary, stand there. Okay, so we're getting closer and closer to the actual Higgs mechanism, but we are not quite there, because people could say, well, it's just some random field, it just has to do with, vector field, right, in our real world, and that's just how always mass is generated through interactions. It's like ubiquitous phenomenon. Basically, if you want, you could read about things called near free electron approximations to the Benson gap phenomenon in solid state. This is not very important comment, but I just want to mention it. So, how conductors work. In usual conductor, we have again atoms. Oh, sorry, I already started joining some atoms of the ion of the lattice. Yeah, they sit in the potential of each other. They don't. They form crystal, and electrons basically move freely. There's an electron waves there. Electrons just run whenever they want in metals. This is called free electrons, conducting electrons. Right? They just would say almost don't care in this near free electron approximation. However, because the atoms are positively charged, right? Whenever electron gets too clear to complete atom, the fact that the total electromagnetic field is screened become less and less important for him, and he feels that, you know, it's here, and instead of just flying forward, just deviates a little bit, right? So the atom creates some sort of binding potential for this electron in the solid, and because of that, the gaps in the spectrum of these electronic waves are open now. The standard phrase for it is that interactions gap in the spectrum, because basically electrons now not completely free. Again, it's a little bit difficult for electrons to just move like this, because these atoms, they hold them a little bit in this kind of, you know, holes like this. Think about it like holes, potential holes for electron traps. They trap them a little bit. So again, it's that has nothing to do with Higgs mechanism at all, but overall on words, it's kind of the same phenomena, right? So basically, very, very careful listeners could have said, "Oh, you didn't explain the Higgs mechanism, right? It's just mass generation through interaction. Just interactions open up gaps. Yeah, it's like we know it." So because of that, I decided that I have to give you completely precise explanation of Higgs mechanism, and it will be the second part of the talk. Before we move on there, I want just to make a last comment here. So don't confuse in these mechanical analogies mass of the field with mass of this balls which was using this in this chain, right? Each metallic ball, well, it has some mass, right? And I assume they were equal. How does it affect anything, right? This mass of the ball has nothing to do with the mass of the field. Basically, imagine my balls are way, way heavy, right? Huge ones, or big mass. Do the same experiment, right? Compress one spring to push one ball to the right, compress the spring. Just right now it's very difficult to do. Basically, yeah, you could just say, oh, it has big inertia, right? But there is no friction still, so it's still moving them, yeah, but kind of slower. And what happens? The spring still contracts, and the next ball, it still has to start moving, and then it starts moving the next ball, and so on. They just all start moving like right? And again, the wave still propagates to infinity in this A1 model, regardless of the mass of the ball, but it moves way, way slower. So this mass of the balls, it corresponds not to the mass of the field, it corresponds to the speed of interaction. In our real world, it's a speed of light. So this microscopic details of our model, they determine the speed of propagation of this excitation, which again, real world will be the speed of light. So just, to clarify some confusions, in case you have them. So the part one is over. Now I'll be moving towards the actual Higgs mechanism. Basically, part one was just explaining what mass of the field is in an intuitive way. Now we'll get to the Higgs mechanism itself, and it won't be easy. So I know maybe at this point you're already kind of tired, and I know your brain was kind of already expecting reward, right? Your concentration is already waning down because well, it's just hard to maintain concentration for such a long time. And then these things were probably not that easy for you, and there's a lot of information. So I just like to warn you that it's not the end. Like, we're just halfway through, and I recommend you to take a break right now. Just, pause the video and, think about the stuff for yourself, or just, have rest, do something else, and then come back, because it's really difficult to watch it like this. Yeah, but I decided to join these two parts together, so we'll just continue. I will walk towards my window for like 3 seconds, and then I come back, and we'll just proceed, because I could just keep going forever, right? So again, see you in 3 seconds, or like 5 seconds. Okay, so part two. Part two is the Higgs mechanism. We'll call it, actual Higgs mechanism. So I decided to write down the precise definition of what happens in mathematical terms, and then I will explain you what each term in the definition means, and I give you concrete examples. There's some confusion which people have about Higgs mechanism. It's important to separate, the mathematical idea behind it, which happens basically in field theory as a mathematical topic, from the real world phenomena. There is a mathematical notion of what we call the Higgs mechanism, which could correspond to several phenomena in the real world, and that's exactly actually what happens. One of the main application is again the description of the electroweak interactions in the standard model. That's what everybody heard about, and that's where you have the actual Higgs boson, right? But it's not the only one. And in fact, today I will be mostly borrowing intuition from a different setup, which is basically a superconductor. Yeah, I decided that it's somewhat easier to understand. But let me give the definition first, and then I will explain it. So the definition of Higgs mechanism is basically, description of what's happening. So it's a relativistic massless field, vector field, I should say. It's important. Interacting with charged scalar field gains mass in the presence of as the non-trivial vacuum condensate of scalar field, of the charged scalar field. eating up. The term eating up I'll explain, of course. So I'll put them in quotes. Eating up one of the scalars, the scalar field, degrees of freedom. Well, maybe I allow myself a bit, definition a bit loose, right? I use some sort of vague terms, but that's the essence. There's a lot of unclear new terms here. I'll have to explain them all. But as you probably already see, it's something way more specific than just, oh, you know, there's a particle, it moves, interacts with other fields, like, and it gains mass. It's not like that. We're talking about some very special scenario, and which will be especially beautiful, actually. Now, as I already mentioned, there are to my knowledge, two main applications of this mathematical notion in the real world. One, as I said, is the Higgs mechanism in the electroweak interactions, and one is the Higgs mechanism in superconducting materials. In the real world, in the Higgs mechanism in standard model, we had this non-abelian gauge fields. Three of them gains mass, and masses, and the photon remains massless. One field corresponding to electromagnetism remains massless. In the superconductor, we have this electromagnetic field gaining mass as well. Okay, it just, you know, this last non-trivial massless field, vector massless field, dies as well, becomes massive. So because in the second example we will have to be working with some intuitively clear electromagnetic waves, I'll start with this case, because I hope you will all have some sort of intuition about you know, electromagnetic waves, electromagnetic fields from, you know, childhood, from your school education, from going to some sort of science museums where you could all play with conductors, charges, and so on. And then we'll try to transfer this intuition into the Higgs mechanism happening in the standard model. So yeah, so in this case, in the superconductor, the vector field in question is just the electromagnetic field. Okay, which you all well know and love. And I would like to point out, it's technically a very non-trivial field. It's counterintuitive. It doesn't have a clear mechanical analogy. The Maxwell came up with his own mechanical analogy. It was confusing. Boltzmann upgraded it. It got weird. Like, there is no simple way I could present it in terms of, you know, chains of balls with springs and so on. No, it's like a electromagnetic wave. They fundamentally propagate in the vacuum. But I hope that you know how they look like. Here, you know, the dimension of our space-time is crucial, because you know that electromagnetic field is fundamentally transverse wave, right? So if the wave travels in the z direction, right, you have only two-dimensional choice of polarization for it. So the vector, the electric field, it could oscillate always perpendicular to the direction of the wave. It could be, yeah, anything here, right? Point in any direction, but it's only two-dimensional choice of options. That's what we mean. So it means you have a two-dimensional basis here. That's what we mean by, you know, the electromagnetic wave having two polarizations. So basically, if you don't know how it looks like, the vector E oscillates like this, according to the basically the sine function, right? Well, I'm sure you've seen this picture many times, right? And magnetic field, if you care about this, orthogonal to the electric field, and also orthogonal to the direction of travel, right? So it's somewhere here, something like this. B. But we will not care about it. So I hope you have some intuition about what a relativistic vector field in 4 dimensions look like electromagnetic field, okay? Now about charge field. What charge scalar field means? Well, as I already told you, the non-charge scalar field means to every point in our space we assign a number, right? Basically think about, you know, non-charged particles. Let's say there's tons of particles in our space, and you look at them from very far away. So you don't see single particles, but you only see, you know, the density of particles. Then in some places there's more particles, and it's like this area is more dense. And somewhere you see less particle, and it's kind of, you know, more transparent. You could see, like, you know, here this like a blob, right, and here just become more transparent, and, you know, you assign the function, you know, particle density to it. Say rho of x, and, you know, it's small here, big here, you know, something like this. This rho is our scalar field. Okay, that's when particles don't have charge. When particles have charge, one function is not enough to describe all information about them, because precisely, you know, you have a density of a particle of charge plus and particle of charge minus, right? And they're like separate. There'll be a lot of positively charged particles here, some negatively charged particles here. We need to treat them separately. It turned out it's more convenient to introduce more like a particle density and a charge density. So, for example, you'll see how it works. If I consider the configuration like this, where I have, you know, I have a lot of particles here, but also zero charge, and, you know, maybe even less particles here, but also zero charge. My particle density to look like this. It's something here, then it goes up because there's more particles here, and then it starts to go down again because there's less particles here, right? But the charge density is, by construction, is zero everywhere. I just, you know, I paired every particle with every positive particle paired with negative particle. So if I draw the graph for charge density, well, you could say there are some fluctuations there, but approximately just kind of zero. Just, you know, maybe a little bit bumps here, or some bump here, but depending on the distribution, concrete distribution of my charge inside these big blobs, which I drew, it's approximately 0, right, in this scenario. However, if we consider, you know, the opposite case, where I have, you know, continuous density of particles, but the charge just changes like this. You know, they span the lattice, for example. Then, if I draw my particle density, it's basically kind of constant, right? Because everywhere has the same number of particles. But my charge density, of course, it changes like that. Here I have only negative particles, right? And here only positive, and only negative again. So here it will be strong negative, then it will change, right? Become positive, and then become negative again. So this is two numbers which describe scalar field. So that's what we mean by scalar field having two degree of freedoms as well. Charge scalar field. Charge scalar field has 2 degrees of freedom to describe particle densities and charge densities separately. So I hope this is clear, right? Now we are moving towards the most non-trivial notion here, which is this vacuum condensate. It's this weird quantum phenomena. So I just want to give you an idea what it will look like, say, in usual conductors, right? In usual conductor, right, we have, as I said, atoms of the ion core, they are positively charged, sitting on the lattice, like this, and electrons fluently traveling through them as waves, somehow, right, like this. Now these electrons, they could scatter with oscillations of this lattice, just like I tried to explain you in the first half of the video. And through this oscillation of the lattice, they start interacting with each other in an attractive way. Again, of course, you could say, well, the electrons usually repel each other because they both negatively charged, but they're surrounded by the atoms of the core, so this this Coulomb interaction between them, they kind of become weakened. So this attractive interaction, so the atoms of ion core, they induce some correlations in different electrons' behavior. So what happens is that two electrons feel each other the most for some reason, and their behavior, their movement becomes correlated. So if one moves here, the other moves there, and so on. They kind of start to move together in a certain way, in a certain sense. And this pair of electrons, which kind of know about each other because of this lattice of atoms in the oscillations, they are called Cooper pairs. And because Cooper pairs is a pair of electrons, now it's a boson, not a Fermi anymore. and the boson, they basically have a possibility to be in the same energy state. And what happens in a superconducting material is that all these Cooper pairs, they sit in the ground state. Yeah, they sit in the ground state, sorry, and in the state of the minimal energy. Basically could say that from the field theory point of view, there's a non-trivial particle density for these Cooper pairs in our material. That's what it means. It's not, there's nothing completely crazy here, yeah, but just they're all in the minimal possible energy state. Which I guess this means that, you know, centers of mass of these Cooper pairs, they're kind of not moving in a sense. Well, I don't know, however, it's might be a little bit, you know, already vague statements. I don't want to push in these directions too much. What's important is that we have tons of these particles sitting in our material. And again, in this situation, the Cooper pairs are charged. They have charge -2 charge of electron, but because of these atoms of ion core, right, the total charge is completely cancelled, right? So this the whole conductor is electroneutral. Now you could say, well, let's study, you know, waves in this material. How will they look like? Will they be massless or massive? Well, we could make an experiment, right? Imagine we have our particle, Cooper pair, somewhere in the material, and we shift it. We pick it again, do the same experiment we always do. We shift it like this, here. And now there is some uncompensated positive charge here. Yeah, coming from this ion core, which means we have an electric field created like this, right? Okay, and all the neighboring particles, the Cooper pairs, and ions, I mean ions are staying still, they will feel it. They will feel this field, and you know what? The negatively charged particles want to attract the positive ones. So the negative charges, they will move a little bit like this, away from the corresponding positive charges, and the material will become a little bit polarized. Okay. Around it. Okay. Now, because of this, this field which I created here, it will be partially compensated because of these little fields here. You know, do you see they pointed into the opposite direction? If we continue these lines, see, they partially cancel each other. So when this field moves through them to say the next line of defense, the particles here, they will feel the sum of this field and this field, and they will react weaker, right? They will move to smaller distance from each other. And again, this creates their own field. And this means this field, when it comes through them to the next layer, right, get even weaker. Now they're almost at the same place. Even weaker. So what happens, as you can see, the original field is what's called getting screened, right? It's getting compensated by these polarizations of each induced in each single atom, in each single point of space. So when it comes to infinity, at infinity it becomes zero. So what happens is the same phenomena, which is this electric field decays exponentially with distance from original excitations when it took these two particles apart. So that means the wave of charge density which I could create in this medium, it is actually massive. Right, for the same reasons I explained the first part of the talk. That happens because the particles are all charged. Now, in case they are very, very careful listener, you could ask me, wait, am I not lying to you? Because these are all electric dipoles, right? And in our model, B1 and B2 were magnetic dipoles. And I told you that, they will feel each other, right? That in a sense that the wave there propagates to infinity, right? And so there is some sort of confusion here. Yeah, that only happened because of the artifact of the model, in the sense that I assumed, remember, it was the essential assumption that only the neighboring spins feel each other. So this spin doesn't know anything about this one, which is in contrast with what we have here, because this was like just a simple model, and this was an actual physical phenomenon. So this is just maybe a little bit misleading, but in case you wondered. So the fact that this field is so long ranged allowed them to allow these particles to feel it even here, and in total it all got screened. So basically you could say that there is an equilibrium position for this excitation to be like next to its atom. So we find out that the charge density wave is massive. Now we could ask the same about our electric field when it enters the medium, how it behaves. But that's essentially the same question. What does it mean to create an electric field in our medium? It just means I bring some charge from outside here. Bringing charge from outside means attracting negative charges here, right? This means we'll have positive charges here, and so on. Which will compensate this field, not allowing to create a wave traveling to infinity. So again, leading to this exponential decay. Again, here it's basically crucial that probably wasn't clear that this condensate is in its ground state, that these particles, they move freely and they react on changes of field basically instantaneously, right? There is no dissipation in this question. In usual conductor, because electrons, they scatter, they dissipate energy, and this phenomenon is not occurring, at least not occurring in the similar way. I mean, it's true that conductor kills electromagnetic wave, but in a different way, which is kind of already hard to describe precisely. That's a difference which is hard to describe. I mean, I'll make a separate video about it. But here, just the main point is that this external field will get screened, just like in a similar way to the charge density fluctuation. So this means both of my electric field polarizations, electric wave polarizations, they become massive. They could not propagate because now my electric field has a potential at every point which make it zero, right? The potential with the equilibrium position at zero, because every time I create non-zero electric field, there is this nasty charges start moving around, creating the one field which compensates my initial one, right? So the equilibrium position for my field is zero, and it takes me non-zero energy to increase my field. So we have a situation where both polarization of my vector field, in this case electromagnetic field, became massive, and the corresponding charge density wave is massive as well. And what happens, mathematically we could merge them together into a new field, which is called relativistic vector massive field, which now has three polarizations: two transverse, like the usual electromagnetic field had, and one longitudinal, which corresponds to the movement of the charge density condensate, right? Because these particles, they don't dissipate any energy, right? They move there freely. When you move one, this information is transferred to the next one with the speed of light, right? So the charge density waves, they travel with the speed of light as well, but they're longitudinal, right? Because essentially what you're doing, you're hitting this particle in this direction. This one, okay, it's negative, will affect this guy through electromagnetic interaction. This guy will affect the next one, and again he will move in this direction, in the direction of the wave. So this is longitudinal. A longitudinal wave. Basically, we have this transverse waves and these longitudinal waves here of this charged density condensate, charge density. They all move together, but they don't travel very far. The initial excitation, the point-like excitation, momentarious, it could not propagate to infinity. I mean, it decays exponentially because of this screening effect. As I said, alternatively, you could think about it like in the momentum space, that even if I'm reducing the momentum of my wave to 0, I still have to do some work, because even if I'm increasing electric field really slowly, like really as slowly as I can, like moving these charges, really slowly, then I still have to pay something. In terms of energy. Yeah, so and as you can see, because it's superconductor and resistance 0, there is no dissipation. So Higgs mechanism is non-dissipative, contrary to the intuition which these examples on the internet might create. Yeah, to here, this was a helpful example from superconductor. I don't know, maybe it was too difficult. Now I could describe a little bit what happens in the real world. So in the real world, we don't quite know the microscopic description of the Higgs field. I discussed it with Sasha Abanov. He told me to think about it as a Dirac sea. You know what Dirac sea is? When Dirac discovered his equation, he realized that the vacuum looks like some sort of old states with negative energy filled with particles. This weird state is called Dirac sea. It's almost like we're living in the world where we have this infinite number of particles constantly filling all states with negative energy. And then, electrons are just particles with positive energy, but holes, antiparticles are just holes in this Dirac sea. It just means somebody took electron out of this sea, out of the state with negative energy, and now there is like a hole moving there. The electrons just jump into it, and from other places, and the hole moves. We don't know whether it's actually true, or just abstraction, mathematical abstraction. But this analogy is useful to play with. We could basically imagine what antiparticle actually is. We could have the intuition of how it behaves when particle and particle collides, right? What happens? Electrons fill this hole, and the energy equal to the twice the mass of electron gets released, right? Because it was here and it drops to m. So we have 2 photons emitted, right, with the corresponding energy. So this intuition helps us, but we don't know whether it's true or not. It's not like it's mathematically consistent. That's what I say. The same for the Higgs field. Like, we don't know exactly what this vacuum condensate is. Is it like a fixed particle condensate, or it's something else? Like, do we have this charged particles everywhere around us? And if they're charged, it's like, why they don't interact with anything? This means this charge is compensated by what? By some sort of atoms of iron core, which just sit somewhere down below at the UV. We could not touch them, or I don't know, just wasn't able to find them on detector yet. So anyway, situation is very similar to superconductor. We have some sort of non-trivial particle density, and they all sit in the ground state in the minimal energy level. And I said that minimal energy level is counterintuitive. It's like, yeah, they probably don't move, but if electric field come about, right, the corresponding field under which they charge come about, they start moving, but they kind of still in the ground state. It's just like, I don't know how to describe it. So in our universe, we have 4 of these gauge bosons, vector bosons, corresponding in this question, which interact with the Higgs field. And the configuration of this vacuum condensate is such that 3 of them gain mass in the way I described above, right? They got screened. And this 3 one is W plus, W minus, and Z bosons, which are responsible for weak interaction. And one, the photon, yeah, it avoids this fate. The orientation of the vacuum condensate is such that photon doesn't excite it, right? It does not get screened by it. So the photon, yeah, remains massless, and that's what you see around. You see photons, right? You see the light. That's why it propagates freely to infinity. So that's, I think, more or less the end of this explanation. I try to make it clear. I don't know whether I was successful. It's probably pretty hard. I try to do my best. Just hope people enjoy the most, intuitive but still yet the most precise explanation what the mass of the field means and what Higgs mechanism means, and how it applies to electrical interaction in the standard model and to superconducting materials in the electrical interaction for W plus W minus Z bosons, and in superconducting materials already for usual photon, which basically screens the electromagnetic field in it. Yeah, I don't know whether this is inspiring or not. Of course, discovery was made many years ago, but I guess it still fascinates people, and I think the mathematical model behind is truly beautiful as well. Well, yes, see you next time.